All right, cool. So 1 second. Oh, you need to. Oh, wait, don't mute it yet. Let me do the intro and then. Okay, cool. So I think we're ready to go. So we're very excited today to have with us Dr. Joe Kiniry, who's a principal scientist at Galois and the research lead of several programs at Galois: high assurance secure hardware firmware design and verification, rigorous systems engineering, trustworthy and verifiable elections, high assurance cryptography, and Audits-for-Good. He's also the principal CEO and chief scientist of Free and Fair, Galois spin-out focusing on high assurance election technologies and services. So again, please welcome Joe, who will be talking about using FireSim for some cool stuff. Take it away, Joe.
How's the volume? How loud do you want me to be?
Yeah, I think it sounds good.
We're good? All right. Good morning, everyone. I'm sorry I can't be there, but I had promised my family I'd go to Mexico for spring break. So I'm speaking to you from Mexico. Otherwise, I would be with you. Thank you so much to the organizers for reaching out and asking me to speak. It's a fun thing to do. It's especially fun because, like, in some sense, Berkeley has had an impact on my career for a long, long time, ever since the days of examining BSD 4.3 in the 1980s. Have I used technologies out of Berkeley for teaching, research, and an industry? So FireSim is just like another milestone along that path over the years. Today, I'm going to talk about a high-profile use of FireSim in a bug bounty program, in particular in DARPA's first ever bug bounty program, which was called FETT. And I'll give you some context around it, as well as some insights into how we continue to use FireSim, Chipyard, and other technologies here at Galois and at our spinouts. I'm not looking at Slack at the moment, so I will take questions from Slack at the end. I don't know if we want to just push all questions to the end. I'll try to leave time for it. So this particular presentation is in the context of one of my DARPA programs I've run over the past 10 years or so, which was called SSITH. SSITH was a program out of the DARPA MTO office created by a program manager named Linton Salmon, who was a fan of Star Wars. So he decided to name the program SSITH, System Security Integrated Through Hardware and Firmware, but we leave off the F. So therefore, of course, most of the teams that bid on performing on SSITH ran with the Star Wars metaphor and came up with all kinds of goofy backronyms matching the Star Wars theme. Our project was called Best Spin with 2 S's to go with the theme of 2 S's in SSITH. The program started in December 2017. It ran for 4 years. And the goal of SSITH was to develop new hardware architectures to actively prevent security flaws and vulnerabilities that exist in software systems. In essence, it was kind of like, well, no one will ever fix all the goddamn software in the world. Let's try to create some hardware that can mitigate some of the problems we commonly see. Some of the technologies that came out of SSITH, as well as predecessor programs that flowed into SSITH that you may have heard about or are getting notoriety today, would be things like the Cherry architecture from Cambridge and SRI, which is now seeing a transition to industry by virtue of work at ARM, Microsoft, and others. The program itself was broken up into 2 pieces. There were a whole bunch of teams all developing different hardware architectures that had security baked in some way, shape, or form, which would mean that they're developing new system-on-chips that have interesting new accelerators or features. And then there was one team, and that was my team, that had to develop new reasoning tools and testing tools to measure and evaluate security of the program and its impact. And that was called the Technical Area 2 team. Now that's where I started. So the first year or more of SSITH was just us developing new EDA tools and infrastructure, and sort of ideas both, at the boundary between chip design and formal methods, which is what, some of my teams do. And about a year in, DARPA said, well, we actually need a platform on which everyone can work and evaluate. And they then evolved the program and asked us to do some more stuff. So Galois was then asked to develop the actual government furnished baseline systems that other teams would take, evolve, add their magic security pixie dust to, and then we would evaluate. And we were asked to develop applications that ran on top of those chips so that we would have sort of targets for evaluation and figure out some way to scale security research on these hardware architectures beyond just the expensive FPGAs we had on-prem at the time. So I'm going to talk about the first and third of these in this particular talk. If there are questions about anything else, I can't overshare on this because almost everything we developed for this particular program has been open sourced. So here's what I'll talk about as we move forward. First, I'll give you an overview of the government furnished equipment that we had to develop for the program and what other performers focused on extending and polishing. Now, all that was originally focused on-prem. So then suddenly they did this pivot and told us, well, now you got to put everything in the cloud. And that's where we got excited, or I got excited to finally get to use FireSim on the project because I was at the original FireSim talk and I was like, that's cool. I want to use that on a DARPA project or a US government project someday. And that gave me opportunity to do so. And then they asked us to build the entire infrastructure for the bug bounty program and help run it. And so I'll tell you about the bug bounty, what it was shaped like, its nature, who participated, its outcomes. And then I'll wrap up with what we're doing these days at Galois in the bigger space of product line engineering for custom, formally assured hardware, software, co-design systems for the government. Now, the government furnished equipment, or GFE, for the SSITH program was basically a whole bunch of SoCs. And they decided that these should all be RISC-V for all the good reasons that we all know. And because in part, Galois was working on RISC-V from the earliest days, mostly in the formal assurance, the formal part of that particular community. And so they wanted 3 different classes of CPUs and SoCs. They wanted a microcontroller and they wanted 2 64-bit things capable of running real stacks like Linux or BSD. One of which needed to be in order and sort of simple, and one of which could be out of order and more complicated. They also gave teams the option of demonstrating multi-core SoCs in the program, but we didn't have to deliver one as a baseline. The performers involved in the program essentially were focusing on 2 different high-level hardware description languages, which brought us joy. So half the teams basically that bid on TA1 were focusing on using BlueSpec System Verilog, and the other half of the teams were using Chisel. In the earliest days, there were some teams also playing with things like HLS from System C and some handwritten Verilog, but they didn't continue in the program after about a year in. So therefore, we had to start off with building 6 different SoCs as best we could on a short time frame, reusing stuff that was already available in the open source community, or developing new things that could help out the community and help out the program. So we needed 6 different SoCs. And originally, this entire program was running on-prem Xilinx high-end, ultra scale 118s, which are reasonable FPGAs to use, although I have to say the VCU 118s are a bit janky when it comes to production quality and the like. The problem is they're very expensive. I mean, these things are about $8,000 a pop, and DARPA bought a few dozen of them for the different performers, but that just doesn't scale. If someone wants to experiment with this infrastructure, they need to not have to plonk down $8 grand in order to do so. Running on top of these 6 different SoCs, we had to build up software stacks that teams could use and extend. Because of course, as soon as you add security ideas into the hardware, you then have to bake that into your software infrastructure as well. You have to bake it into maybe firmware, device drivers, and even compilers, linkers, and the like. So we built on top of the 32-bit SoC support for FreeRTOS as well as bare metal programming. And on top of the 64-bit SoCs, both support for Linux and FreeBSD in the program. The big picture architecture of the SoC in the general is in the lower right-hand corner. So pretty much all of them have nearly the same I/O, nearly the same interfaces to DRAM and the like. They all do have network connectivity, programmable and debugging connectivity and the like. That's all fairly familiar. And you're just plopping in different shaped processors in that box in the upper left. And then on the top, we have something called the Security Verification Factory, which you can think of as runtime introspection into the microarchitecture of the CPU. to help performers do things like write interesting assertions that really need deep information about the CPU as it's running to do runtime assertion checking of a system on chip. So think of it as building 6 of these, and the program manager comes to you and says, I need this in 4 months. And you're like, holy crap. So of course we have to use what's out there that we already knew as best we could. And the Chipyard ecosystem at that time, already existed. There were already some good things in it, although it hadn't matured to where it is today, because we're talking about, what must have been late 2020. And so we scrambled around and figured out what the right things were to do with regards to reusing things in Chipyard that were in Chisel, like Boom in particular, as well as figuring out what was available in the BlueSpec community, because we've worked with BlueSpec for many, many years, and figuring out what to fund there in order to build new CPUs. So basically all the new CPUs that you've seen out of BlueSpec over the past few years, name things like Piccolo, Flute, Tuba, and the like, were all funded by this development effort. And they're all meant to be, sort of pseudo-isomorphic to the corresponding CPUs that came out of the Chipyard community in Berkeley. Now, when you get told you need to build 6 of these with the whole OS stacks and the compilers, which has to include both GCC and Clang support, and you have to move it to the cloud in 4 to 6 months, you can't just say that's going to cost $20 million and throw a bunch of people on it. That's not how it works. That's not how we work. And so this gave us an opportunity to reuse FireSim, as well as to use some other technologies that were coming out of our team as well as MIT to move stuff to the cloud. This means that we had to move from a GFE that was just on-prem to a GFE that could run on Amazon. The government chose for us to use Amazon, and we already had some familiarity with it, but we had never used F1 instances at that point in time. And so we had to reformulate the GFE into CloudGFE. And it had to do all the properties that were already mentioned earlier in terms of giving you on-demand, anywhere access to simulation in the cloud. And we had to scale it to not just the number of teams currently working on SITH at that point in time, which would have been something on the order of 6 to 7 different teams, each of which had a number of performers there. But also DARPA at that point in time is where they hinted to us they may be doing a bug bounty. So we knew we'd have to scale to hundreds of instances, if not more. The coincidental nice thing is that the FPGA we had picked for the program happens to be the same one that's in EC2 F1 instances. But, kind of everything that we had been building so far was designed for running software stacks on rich full RTL sims in on-prem FPGAs, and we weren't doing much, if anything, of sort of software sim of IO units and similar, like you just heard FireSim provides possibilities of. So we had to move and pivot to all that. So how do we use virtualized peripherals like you witness in AWS, rather than physical peripherals that are literally plugged into a PCI bus? We needed UART, Ethernet, file systems, random number generators, etc. And we had to make sure that entire stack works exactly the same. If I've got it on my desk and I've got a PCI bus plugged in, and I've got an FPGA card plugged in there, and I got a USB card plugged in there, and I have a block device plugged into the USB as well as a mouse and a keyboard, it has to work exactly the same from a software point of view if we do it in the cloud. So we chose to use FireSim for all the chisel stuff, and we chose to use originally something called ConnectDoll from Jamie at MIT, which was built in part on top of VirtIO stuff, as well as evolve that into the BlueSpec ecosystem, and that eventually became an open source project called Austeria, which you can think of as VirtIO for BlueSpec sorts of development and sims. And that has evolved to a new product from BlueSpec as of today. There were a whole bunch of other challenges, of course, when moving from on-prem to the cloud, because you need to make sure that things behave the same from a security point of view. And when you're moving to virtualized devices from physical devices, it's a heavy lift. And so that took a lot of hard work. Now, we started moving it there. And one motivation for doing this is to let more people work on top of the government furnished equipment in the program. It also let other government parties who are interested in things happening in SITH get access to and play with SITH technologies without buying these $8,000 boards. But they also floated the idea that maybe we'll do a bug bounty. Now, we didn't think at first they would do this because DARPA had never run a bug bounty before. And in fact, a bunch of us aren't very hip to red teaming and bug bounties for a variety of reasons. But it was a nice public way for them to demonstrate the technology as well as to get people to poke and prod at it. Certainly there were companies already doing this kind of thing, but they're not going to share their results publicly, and who knows how much they'll invest in it. So this is a way for government to do kind of a big splash with regards to trying to assess the actual security of these systems. So they decided to do so by setting up a bug bounty program that was completely independent, run by a different entity with researchers that already had some chops in terms of analyzing complex systems, in a controlled environment where they could gather all the data they wanted about what people were trying, as well as keeping researchers' identities private. It turns out this is a thing that white hat hackers working for these kinds of companies don't want to identify themselves for one reason or another. So this meant we had to build an entire infrastructure to support this kind of thing. So let me review what this infrastructure looks like and how we built it and where FireSim fits into it. So this was DARPA's first ever bug bounty program, and they decided to work with a crowdsourced red team to stress test the entire system. They worked with a company called SYNAC, or we worked with a company called SYNAC to set this stuff up. And we need to, in the shaping of this bug bounty program, we need to do it in such a way that it both gives some degree of validation about the new kinds of security IP that's developed in these hardware stacks, but also gives some validation about the work we had done on whether or not, if you run our tools on a system and it says, hey, this thing is really secure, then you should see some sort of loose correlation to the behavior of the red teamers and their successes. So if we think a particular system on chip isn't very good, then you would expect people to find problems with it. In the end, at the top level, almost 600 researchers participated. They ran tons of instances of these systems over the course of several months, and they found some vulnerabilities. And I'll summarize these in a moment. The systems, the actual Tier 1 teams that were involved were the ones at the bottom in the chart. So Lockheed Martin, as a defense prime, had a 32-bit microcontroller. That was kind of an IoT-like device. And they ran on top of FreeRTOS, and they basically built something that resembled an over-the-air update client. And so your goal there was to try to violate the security properties of this particular secure boot over-the-air update application. Todd Austin's group at the University of Michigan had a 32-bit version that was running an open database server that they built on top of FreeRTOS. So there was opportunity to sort of have a database point of view attacks on the system through a web interface. I should say all these software stacks that I'm mentioning that are running on top of these systems are all not only open source, but are actually seeded with vulnerabilities. We know there's known vulnerabilities in them, and we enumerated those for the attackers in voluminous detail. They knew exactly where the flaws were. They had all the software stacks almost for the entire program outside of some of the Lockheed Martin stuff. And so they know where to look. Lockheed Martin also had a 64-bit CPU instance that was running Linux. On top of that, we were tasked with building a buggy voter registration system so that people could try to hack a voter registration system where you would register voters and update their records. It was very much in the news. Remember, this is 2019, 2020, right before the election and the like. So DARPA leaned into that a bit. And on top of that was a whole bunch of Debian Linux, random applications that had flaws in there. We basically picked an old version of Debian that we knew to have a ton of CWEs and CVEs in it and enumerated them for attackers. MIT had a 64-bit CPU, which was running the enclave that they developed on top inside that secure enclave. So this is from Adam Chapala and Arvind and Srini working together with their students. So they had an AES engine in there running in a secure enclave. They did a whole bunch of stuff around authentication modules for Linux, and it was running Debian on top. And then the last team is the Cherry team from Cambridge, SRI, and some others, which also ran that same voter registration system, but this was on top of FreeBSD. So we get 3 different OSs involved in the overall shape and nature of the system. The infrastructure looks like this. This is kind of a classic amalgamation of AWS stuff. This is my first occasion to actually learn and use AWS, and basically it became a lesson in figuring out how to map Amazon trademarks to computer science concepts, which drove me a little bit crazy at first. AWS is a client of ours, so we have worked with Amazon for many years. Galois is the team has been doing for many years the formal verification of all the crypto that runs in AWS that all of you use every day. So we already had some familiarity with like the internals of at least the security side of AWS, but we hadn't used all this stuff like AWS Lambda and EC2 and blah, blah, blah. And so we had to learn all that and work with a team that knew that really inside and out to build this system. Essentially, we need to build a system that people could log into and automatically spin up and down instances to run their red teaming completely independently, but also track everything they do, record it all in a privacy-preserving way and the like. We worked with Synac on this, which is a reputable crowdsourced security company. They already have hundreds of researchers who work, what they call security researchers, who work there and attack systems. And we tried to, leverage that community to get good engagement on this program. And so that they provide access to all those researchers, and then we have to basically hook all their infrastructure, which runs in the cloud as well, to the CloudGFE targets, running all these different OSs. The dashboards that were created to do this, give a user experience to the researchers they're familiar with from previous bug bounty exercises, which are a bit more boring and don't involve novel hardware, and also has to do all that logging that I mentioned before, and provide all the educational resources necessary to bootstrap people so they could actually attack the system. There's a tool inside of all this that's kind of like, in some sense, it's like FireSim, when FireSim moved from on-prem to supporting cloud, going from cloud to on-prem, we went the backwards way. So it's a tool called FETT that kind of spins up all these things, sets up all the infrastructure, does everything automatically behind the scenes, sets up all the network infrastructure, all the VPNs and all that nonsense. The access points provided for attackers to attack depended upon whether or not they were running one of these processors, these 3 different scales of processors. For 32-bit processors, basically they had direct access to the UART, direct access to the over-the-air update system with a documented protocol, as well as a web server running. And for P2, they had access to the UART, to the web services, and SSH. So you get credentials. You get to log into the system and load whatever programs you want to build on your local system. You can load them into this remote instance and try to violate things. This includes root level access to the system. So you can, it's DARPA basically saying, in a real bug bounty for real world systems, you have to presume that A, the adversary already knows your system, already knows your architecture, already knows your software stack, etc. B, they're already behind the firewall, they're already in, they already possibly have root level access. Let's see how bad it can get. So it's a very, very robust threat model for the bug bounty program. The portal looks like this. Basically, security researchers working for Synac are able to log into a dashboard. They can see access to all the different kinds of processors they can spin up. It all has these code names to make everything anonymous. They can spin up multiple instances simultaneously, and they're all characterized in various ways. I have to redact some of it, I'm sorry, for the gray areas, but that gives you an idea as to what it looks like in its shape and feel. And the dashboard shows you like when things were launched, what's running at the moment, what's been terminated, where can they get their own logs to dump out resources from the spin-ups, all this kind of thing. And then baked into the website is essentially something that kind of looks like the FireSim documentation, except we had to document all these different teams and all their resources, teach them how to use the system, how to spin things up, how to access, point them to all the different public artifacts that were involved with every single system, even have little tutorials and little demos of how to attempt to cause harm. Some of the CPUs that they can spin up are unprotected CPUs, so they can compare and contrast the baseline CPU and SoC with the protected one. They could develop exploits on the unprotected one, see those exploits work, and then try to pivot them or get new footholds in the secure system that was an evolution of that original one. Pretty much everything was public. The only thing that wasn't public was some artifacts relevant to Lockheed Martin's design, which is unsurprising given their defense prime, and they're trying to create something that is novel for them and isn't going to be published. The contest ran for 3 months, so people got to take a considerable amount of time on this. That's kind of what I would consider a shortest legitimate red team of this nature. It ran during the summer when people were purportedly going to be more available. That's how we scheduled it. In the end, there were 4 research teams that had processors in the cloud. There were a few others involved at the time, but their stuff wasn't mature enough to be involved in the red team exercise. And as I mentioned, around 600 researchers participated. About 1,000 different instances were started. A bunch of hours of hacking analysis were done. They identified 10 different valid vulnerabilities, and there were payouts for such, and I'll explain what that looks like in a moment. But most of the vulnerabilities basically had to do with firmware, is where it boiled down to things. People rarely found anything of interest in the hardware designs, and I'll explain why in a moment. Most of the time it had to do with that hardware-software interface and the fact that most of the industry, and even a lot of academics, they say words like hardware-software co-design, but they don't really mean it, especially with assurance. There's only a small number of teams, like my team at Galois, that do that with vigor. There were a bunch of vulnerabilities discovered during the course of the program, and they were actually patched and verified during the course of the program. So the teams were actively involved in supporting this effort and working on top of this infrastructure. Now, I can't disclose how big the bounties were, but they were, SYNAC has some standard bounties for like exercises of interest. So you're going to be paid reasonable amounts of money for your hard work if you find something. And DARPA really wanted researchers to focus on this rather than sort of the classical stuff that was going on for other activities at SYNAC simultaneously. So they set the initial bounties at 2 times bigger than anything that people would have seen traditionally. Part of this is to get their attention, and part of this is to recognize that attacking a system with novel hardware and software is harder and requires a different sort of skill set and dedication to just doing a standard pen test on an application stack that's boring running on top of a CPU you used for years. After a few days, after about a week, they evolved the bounties so that pretty much any in-scope vulnerability got a high payout. And there was a bonus if you could find a vulnerability on all 4 architectures as a single researcher or researcher team. About 3 weeks in, they bumped the bounty value again. And on day 55, they bumped the vulnerability on Cherry in particular, because a lot of people had a lot of interest in Cherry with regards to its novelty, its potential for transition, its potential in the DoD. So they wanted people to really focus on it. And on day 61, based upon results they had already seen, they decided to stop the engagement on the Michigan and MIT processors and focus solely on the Lockheed Martin and Cherry processors. And so on the right, you see sort of the graph of activity on these different areas, and you can see how there's inflection points when you offer more money. We also introduced missions as we went through the program. It's one thing to give people sort of an open scope to do anything they want. It's another to point them in the right direction. And sometimes you get different kinds of engagement for that. So for example, we introduced a specific mission on top of the Lockheed Martin processor 3 weeks in that was on their over-the-air update system, which was on top of a TFTP server. So this let people focus on one specific protocol on one specific application stack running on top of FreeRTOS. Day 23, we pivoted that to include some more stuff on top of how the Lockheed Martin processor worked. On day 35, for example, we introduced some additional information around the SQL interface on the Michigan CPU. And then on day 57, we did a whole bunch of separate campaigns around different facets of the Cherry architecture. And each of those helped with inflection points and helped people focus. 10 valid bugs were found. As you can see, they span almost all the systems. Most of them have to do with firmware that was sort of traditionally written, as opposed to the hardware which was novelly created. But some of them did include some hardware flaws. The reason I differentiate between the firmware and the drivers and the hardware design is that teams like MIT and Cambridge in particular used formal methods as part of their hardware design. So they had real rigorous assurance around their systems, kind of both at the architectural and microarchitectural level, as well as with regards to the actual implementations. You know, much of the MIT system, the hardware design that is, was automatically synthesized from COC, for example. And so they had a lot of confidence that pieces of that particular hardware architecture had exactly the properties they thought they did. But then when you build on top of that and you hand write some firmware quickly and you don't do any reasoning about the firmware, you're bound to make mistakes. That's kind of what happened in this particular instance. Much the same sort of thing happened with the Cherry instances as well. You know, a lot of it had to do with Cherryization of things like the memory management subsystem and BSD, some edge cases in the linker and then the compiler and similar, and a couple of little things with regards to the design of the hardware system were found. I was, you know, on the one hand, I was impressed that some researchers found these things because it was, you know, it's quite a lot to learn to go from zero to hero and try to do this kind of exercise. On the other hand, you know, with more dedication, you might find more because these are complex software, hardware, co-design stacks that do interesting and novel things. And so I was, you know, pleased at the outcomes of how this particular exercise went and how we did get some results. But I was more pleased about the fact that this triggered industry to be especially interested in some of these architectures and potentially transitioning them to industry. And so additional red teaming effort has spun up with gusto at a variety of different large companies that you know. Now, the reason we got as far as we did is that, but you know, there were some limitations, is that the typical research engineers that do security research for SYNAC are really heavily skewed towards software folks. You know, they know a couple of different traditional CPU stacks. They understand like certain ABIs, certain ISAs, but they would have never maybe used a RISC-V system before. So some of them just got involved because they wanted to learn RISC-V. Also, you know, typically, at least for the sort of low to medium grade experts in this community, it's a lot of traditional pen testing where you have a stack of different tools that you pull out and you use, and there's very little real novel 0-day sort of stuff going on in this sort of setting. But we did see some good traction. So as I mentioned, 7 out of 10 bugs were, you know, basically in firmware and a bit of stuff in hardware. And yeah, and we kind of got correlation that the things that where people used applied formal methods to develop CPUs and where my team's tools and techniques were used to evaluate a system, and they said, this is really good. Indeed, we didn't find flaws in those parts. We found flaws in the parts of the system where my team's tools and analysis said, here's where you should look, here's where you should be concerned. And that's indeed paid out in practice. 3 out of the 10 bugs were in hardware, but they were basically exemplified by behaviors in software. So the researchers didn't really have to understand how the hardware worked. It was kind of a black box that behaved improperly from a software standpoint. And so most of the researchers described their exploits from that point of view. And really, the researchers struggled with finding any meaningful attacks on microcontroller class processors. For the most part, SYNAC red teamers work on 64-bit systems that are multi-user. Rarely are they ever paid to focus on an IoT application or that scale of application that's running bare metal or running an RTOS. Most of them have never attacked a system that runs like a typical industry RTOS that's out there in the wild. And you know, the interactions with that kind of CPU are more limited than you are used to. And so it requires a different sort of thinking. Now, I've described where it went in this particular program. Now I'll describe where it is now and where it's heading. This FETT tool and all this infrastructure we developed was all open sourced. It's got abstractions in it that permit you to target different kinds of hardware processor architectures and extend it in various ways. It supports not just this VC118 and F1, but also QEMU for fast emulation without dedicated hardware. Also, of course, it plugs into the open source ecosystem around software sim and similar if you want to simulate more detailed but slower simulations, a la Verilator and the like. And it's got a bunch of extensions in there to support multiple targets simultaneously, you know, sort of the product line that I described of hardware designs, ISAs, compilers, and operating systems all in one framework. So, you know, DARPA has made noise about maybe doing a bug bounty in the future of a similar shape and nature, and it'd be wise for them to build it on top of this existing infrastructure. Now, we continue to do work in hardware-centric R&D at Galois these days, some of which is spinning out of this work and reusing some of this stuff. Many of the projects I run continue to use Chipyard. We continue to use FireSim in various ways. Most of these aren't things that I get to talk about publicly other than summarizing them, though I always try to convince the clients to let me open source things and talk more vigorously about them. The 4 projects I can summarize here that are running right now or just completed in the past few weeks that touch upon these things to give you a shape and nature of what we do and why we use FireSim would include a project for the Space Defense Agency called Hyperspace. Yes, I know most of you have never heard of the Space Defense Agency. I encourage you to look them up. They're a real thing. Hyperspace is about developing a high assurance, ultra high performance cryptographic accelerators for space-based applications. So you can think of it as how do you do formal methods, product line engineering of model-based generation of fancy crypto accelerators is a way to think about it. The second project is called Hardens. It was recently completed and open sourced. It is a high assurance protection system for nuclear power plants for the Nuclear Regulatory Commission. It's FPGA based. It has a formal assurance case that spans software through firmware all the way down to a formally assured formally assured CPU and a rigorously validated system on chip that is a RISC-V based architecture. The third project is a tool project. So one of Galois' popular tools is called SAW, the Software Analysis Workbench, which is kind of now evolving into the System Analysis Workbench. It's a tool that lets you basically reason about software in the old days. We have extended it over the years, now starting to do that publicly about reasoning about hardware as well. So you have one tool in which you can reason about equivalency and refinement of software, firmware, and hardware. SAW is able to lift models out of binaries, like things like ARM and RISC-V. It's able to lift models out of LLVM, JVM, and now it's able to support pieces of, sometimes large pieces of various hardware design languages. This means, for example, I could prove mathematically, automatically, that a given implementation in system Verilog is equivalent to a formal specification written in like the Cryptol language that we support that works with SAW, or for that matter, say, you know, something written in Java, as crazy as that is. Lastly, we have a project called Basilisk, which is for DARPA, for the DARPA MTO DPRIVE program, which is developing a high assurance, fully homomorphic encryption accelerator. So an FHE accelerator. This is an accelerator that uses crazy crypto that can basically compute on encrypted data in an encrypted fashion all the time. It's the biggest thing we've ever built in terms of an ASIC. It has inside of it a whole bunch of stuff from Chipyard. It has RISC-V CPUs. It has the, as far as I know, world's biggest formally verified multipliers and other matrix operations in interesting ways. And we're in physical design right now. Each of these hardware systems that I've mentioned here is formally modeled from soup to nuts so that we can run them as a digital twin in simulation using things like Cryptol and other applications. We then synthesize from that HDL of various kinds, things like BlueSpec as well as System Verilog. And then from there, we go into other design flows. The other novel thing about these systems, especially when we do tape outs, is that we use an asynchronous design flow. So most of our chips, all of our recent chips don't have a global clock. We use an asynchronous design flow that's influenced from my old work 20 odd years ago at Caltech, as well as new work that we do with USC and PSU on this topic. So that concludes my talk for summarizing the FETT bug bounty and how we use Chipyard and the like. I'm happy to take questions about any of this stuff. One thing I will say is that I continue to track what's going on in this community with vigor. You know, we actually use a tool called Hammer these days to formally generate software from systems architecture specifications and reason about it in the software world. And now there's a hammer in the hardware world. I want to have like 2 hammers in my hands for a next project. So I've been tracking that. We've been tracking and playing with things that come out of the DARPA POSH program, like Open Lane and Open Road. I would like to incorporate those into our design flow some. That would be a lot of fun. We are following the stuff going on in the LLVM community about hardware design with CERC and similar things, and I'd like to include that in a future project. But in general, you know, we love working with and leveraging the outcomes of excellent research from the academic community. And I look forward to working with Berkeley and others some more on this topic into the future. The one big thing that's happening right now that I highly recommend people in the room think about is how might you do things like FireSim, where you're attending to not just measures like power performance and area, plus now we can do security by virtue of SSITH, but how do you attend to side channels? How do you do FireSim for side channels is a big thing, and the government would love to do that. I'm working on some programs now on that topic. So that's about it. I'll happily take any questions that the audience has now or that are on Slack.
Awesome, thanks, Joe. Can you hear us?
Yeah, I can hear you just
Great.
fine.
Yeah, thanks for the awesome talk. That was super cool. So I will start off with a quick question. So did any of the attackers break anything in the infrastructure or FireSim by accident?
No, actually, FireSim was extremely robust in this instance. You know, we had to do some custom mods on top of it to support the infrastructure and the like, but I was really pleased with how well it worked. The attackers had a very strict remit about they can't attack the infrastructure and the like. Okay. So of course there would be a concern that you accidentally break something, but we were, you know, I think we did a pretty good job, and you all did a good job in supporting us. And it led to, you know, no outages for the entire thing. You know, we were up 99.99 and the like, and you know, it's kind of a miracle by virtue of how quickly we had to build it. So no, nothing came up that caused us a heartburn.
Cool. Any questions in the room?
What is Slack?
Oh, on Slack. You want to just read it, Jared?
Yeah.
Or no, read it in the microphone. Yeah.
All right. Hey, Joe, this is a question from the room. I'm an experienced grad student trying to choose a microarchitecture simulation platform for my master's thesis work. Could you perhaps compare and contrast anything with the Chipyard and FireSim and the BlueStack Austeria stacks?
So that's a great question. And, to facilitate, I could put my old professor hat on and answer it from that perspective, but we get the exact same question from industry. We have to recognize that in general, in industry and in US government development work on new hardware architectures or new hardware platforms, whether it's an ASIC or FPGA, most of the industry is stuck in the late 90s, frankly. They look at things like Chisel and they don't even know where to even start. They're scared of software. They don't know what functional programming is. They don't know what a trait is. They look at BlueSpec and their eyes cross. So in general, we support 3 different styles of design flows that come out of these different sort of pseudo mainstream communities. A moderately, so a master's student who is interested in getting into this can either go about it like tackling it from a purely open source experimental ecosystem, just leaning into old school stuff. So you could just use Verilog and System Verilog, and there's a rich ecosystem of tooling, existing CPUs and SoCs and the like that you can use there. So that's one way to go, and there we would use things like Verilator. We use YoSys and we work with them a ton. We would use ABC. We would use IP that came out of the DARPA POSH and IDEA programs and similar. And that would be a perfectly legitimate way to learn about this topic and build things. And if you get really, really good at System Verilog, you're ahead of most of the industry. Like the industry doesn't even use System Verilog very much in the mainstream. If you want to go something outside of that and lean into a modern HDL, then your 2 big choices are basically these days Chisel and BlueSpec. I think there's something really great about learning and using both. Both have open source infrastructures these days. We finally convinced through one way or another BlueSpec to open source everything. The 2 languages teach you a whole lot about how you can think about and reason about hardware. The tooling available to both is rich and high quality. I would say the documentation in the BlueSpec universe is better simply because they've been a company for almost 20 years and they've had to support corporate stuff. So in releasing all their stuff, they have a lot of rich documentation, whereas the ecosystem around Chisel and the like, it's gotten better over the years, but it's still the case that to really get into it, you have to come from a place of having a direct connection to the community or growing up in it or similar. So if you're a master's student at Berkeley, it's no problem. If you're a master's student at North Dakota, it might be a little bit more challenging to learn and wrap your head around the Chisel ecosystem and Chipyard and the like. And part of that is also because the richness of that ecosystem and the ideas in it mean that when things work, it works well, but when things break, you're lost. It can be really difficult to debug when things have gone wrong with any sort of rich, high-level programming language and infrastructure. Debugging there when something goes wrong can be as bad as debugging in C++ or Haskell in our experience. So, personally, I think there's something to learning all of them, but then again, I think, when it comes to learning like object-oriented programming, you should probably learn some clean, nice languages and some awful ones at the same time. This is sort of the same sort of feel. So I would say lean into that which you have good connection to community with and aligns with your joys. And don't worry so much about how it looks on a resume with regards to getting a job, because learning about any of these sorts of things, even the high-level languages, is going to teach you about the mess that is Verilog and System Verilog and the like too, and that brings you value to anyone in the community.
Thanks.
Yeah.
Awesome.
Any other questions?
Yeah. Any other questions? Otherwise, we are right on
I have
time.
one more thing to say then.
Yeah.
So firstly, you can see all the cool things that we do at Galois. We are hiring all the time. So if anybody's interested in learning this kind of stuff, you can come talk to me. Second, and that doesn't mean you don't have to be American, you don't have to have clearance and all that. That's only a little corner of what I do. We love to open source stuff. So, we've got over 500 repos on GitHub. Go look to see the kinds of things we do. I did mention out loud that there's a lot of activity around reasoning about simulating systems where we can measure side channels. So if anyone's interested in doing that with me, I have clients. And lastly, one thing that I think the community really needs that we don't quite have yet is, Chipyard, FireSim, and I presume Hammer, but I haven't used it yet, are really great tools and are really great infrastructures. And it's great that they're open source, but we don't yet have a Red Hat for them. We don't yet have a corporate entity willing to stand up and support them. And I've been asked, like Galois has literally been asked, can we pay you to support Chipyard for government? And I'm like, I've got a bunch of performers that could do that, but they're actually solving problems and doing research. I don't have the scale in order to do that. If we could figure out a means by which to create an entity, a nonprofit or corporation or something in the community to provide commercial support for these kinds of things for real world deployment, I think it would accelerate transition tremendously. And if you're interested in causing trouble on that topic, come talk to me.
Oh, there's another question on Slack.
Yeah,
can-
if you have time,
Yeah.
could you talk a bit more about what are areas of interest in FireSim plus side channels, attacks, effective
Yeah.
defense, both?
So let me be delicate about it. We all know side channels are a thing. People have focused a lot on side channels for crypto in hardware and software implementations. There's entire conferences ripe with attacks here. Government's concerned about it. The side channels I'm talking about include digital information leakage through interfaces, timing side channels, as well as various forms of physical side channels. So power, energy, RF sorts of things, heat, etc. There are some new technologies that help you simulate ASIC designs, as well as roughly simulate RTL designs to get some gauge of how much leakage there is from a given sort of system, including like full simulation of a GDS layout in a particular process. The problem is that it's extremely expensive. To analyze even a small ASIC to check whether or not some side channels might exist, if you presume that you're doing some mitigations around it, can cost a whole lot more than FireSim costs to simulate stuff at RTL. But the government knows that they really need to build systems that don't leak. And so we're stuck between a rock and a hard place. Either you're spending tens of thousands of CPU hours on a single design point to see if it might leak, or you're getting very rough numbers and you're sticking your thumb in the air and you're spending millions of dollars to tape out, and then you do post-silicon analysis. So right now, what folks really want is something between those two worlds that gives us confidence, but not perfect fidelity, without the need to do full physical-based Monte Carlo plus finite element method simulation of ASIC designs. That's the sweet spot. And it has to attend to this whole breadth of side channels I just mentioned. So you have to be able to attend to the 7 different side channels that the government cares about. Right now, there are people who are building things that are meant to mitigate this, but if you have no way to evaluate it except for doing a tape out, it's just too long and too expensive and too risky. The government is just these days not willing to drop millions of dollars to tape out something at an advanced node on a shared run, get it back, spend another several tens of thousands or hundreds of thousands of dollars to see if it runs right or leaks, to find out it went wrong. It's just not a thing. I've been working on this topic, and I've given some public presentations about it, about the work we've done on it. There's a project called 21CC, which stands for 21st Century Cryptography, which is about our way of tackling this program for DARPA and the NSA. And I'll be giving a talk actually on that at the upcoming ERI Summit in August. So if you'd like to see where we've come with it and what the challenges are and where we think there's real opportunities for doing things like formal reasoning about architectural designs and RTL without needing to go to physical design, and how that might intercouple with the sorts of SIM techniques that exist in FireSim, you can come to that talk in August. Or reach out to me and I'll share a sneak peek.
Awesome. Any other questions? All right. Thanks again, Joe, for joining us despite being on vacation. Hope you enjoy your
all good.
vacation. Yeah.
And I do promise I'm not going to participate the rest of the day. I'm afraid I'm going to go out with my family.
Yeah,
and all
totally
that.
understand.
But I'm gonna totally look at all the talks and look at all the papers and follow up with people as I normally do. So don't be surprised when I reach out and say, hey, would you like to partner on a thing? You can write 3 pages and I'll give you $250,000. So
Awesome. Sounds great.
cool.
Thanks.
All right. Thanks all. Appreciate you.